Welcome to The Curious Machine. Today, we're plunging into one of the most fascinating and, frankly, a little unsettling ideas I've ever come across. It's this claim that people who lived just a few thousand years ago, well, they might not have perceived colors in the same way we do today, specifically the color blue. I mean, some even suggest ancient Greeks couldn't see blue at all. It really makes you wonder, doesn't it? Is it true that we've only, recently begun to perceive blue? And kind of related to that, why does it seem that the color blue is so incredibly rare in nature compared to other vibrant hues we see everywhere, like reds and greens?
Those are, yeah, truly intriguing questions. And that's precisely what we're going to try and unpack in this deep dive. Our mission today is really to go beyond the surface, explore the physics of light, the biology of our vision, and even the cultural history of color perception to understand what color truly is, how we see it, and why blue holds such a unique and, well, perhaps misunderstood place in our world.
Okay, let's start with what feels like a real head scratcher, these ancient texts. You come across famous descriptions like Homer referring to the Mediterranean Sea not as blue, but as wine dark. Now, if you've ever seen the Mediterranean, that comparison just feels, well, odd. Why would he choose such a peculiar description for the ocean? What does that even mean?
Right. That's where it gets truly fascinating.
Yeah.
Researchers like William Gladstone and later the philologist Lazarus Geiger, they really dug into this. They meticulously studied a huge range of ancient writings, not just from ancient Greece, but also Icelandic sagas, ancient Chinese texts, even ancient Hebrew versions of the Bible. And what they consistently noticed was this striking absence of mentions of the color blue. While colors like black, yellow, red, and green were described in various ways blue, it was almost entirely missing from the vocabulary. Geiger, in particular, he observed this remarkable pattern in how color vocabularies evolved across different languages. Historically, it seems every language first developed words for black and white, or maybe dark and light. Makes sense. The very next color to get a distinct word was almost always red. Which again kind of makes sense given its association with things like blood or wine, very important things. After red, languages typically develop words for yellow and then green. But the critical point, the really interesting bit, is that blue consistently appeared last in the color vocabulary of cultures worldwide.
Wow, that's a truly puzzling pattern. If blue consistently shows up last, what does that fundamentally tell us about its perception, or maybe just how useful it was to early humans? And there's an interesting exception in all this, right? The ancient Egyptians. Yeah, they seem to be the only ancient culture known to have both a word for blue and the ability to actually produce blue dye. So the big question then is, if a culture didn't have a word for blue, does that truly mean they didn't see the blue of the sky or the ocean? It's a profound question about how language might shape our reality.
It really is. And to get at that, we kind of need to understand the science of color itself first. Fundamentally, color isn't like an inherent property of an object. It's our visual perception of the electromagnetic spectrum. Light waves hitting our eyes. Our human eyes are trichromatic, which means we have three types of cone cells in our retinas. These are our primary color sensors, and they're tuned specifically to red, green, and blue wavelengths of light. These cones process the light that hits them, and then our brain interprets those signals as color. But it's really important to remember that not all animals see color the way we do. Bees, for example, they can see ultraviolet light, which we can't. And the mantis shrimp, it has an incredible 12 types of color receptors. Hard to even imagine what that's like. Now, when it comes to how colors are actually created in nature, there are basically two main ways. The first way is through pigments. You can think of pigments as tiny chemical filters. They're molecules with a specific structure, and that structure allows them to absorb certain wavelengths, certain colors of light, and reflect others. So chlorophyll, for instance, the green pigment in plants. Its molecular structure absorbs almost all colors except green, which it bounces back to our eyes. That's why plants look green. Melanin, the brownish-black pigment in our skin that absorbs most wavelengths of light. Now, the reason blue pigments are so rare in nature, it comes down to energy. Blue light corresponds to a relatively high energy region of the electromagnetic spectrum. And it turns out very few naturally occurring atoms or carbon-based molecules have the right properties to stably reflect these high-energy photons without also absorbing them or breaking down. Now, sure, elements like cobalt and chromium can reflect blue, but they are often toxic to living organisms, and life on Earth is primarily carbon-based, so finding carbon-based molecules capable of producing a stable blue pigment is just generally very difficult for biological systems to create or use effectively. This is why truly blue pigmented creatures are such a rare find, like some olive-winged butterflies or those blue-footed boobies. We even see some interesting workarounds, like the horseshoe crab. Its blood is actually blue because it uses a molecule called hemocyanin, not hemoglobin like us, to carry oxygen. And lobsters, they're blue before cooking right. They achieve that color by linking up a naturally red molecule called astaxanthin in a certain way. When you cook the lobster, the heat breaks those bonds, releasing the red astaxanthin, and boom, the lobster turns red.
Huh. So, okay, if creating blue through pigment is so incredibly hard for nature, chemically speaking, what other ingenious ways does life find to create that vibrant blue we sometimes see? There must be another way.
Yes, exactly. That brings us to the second primary way colors are created in nature, completely without relying on pigments, and that's through structural coloration. This is where the surface of an object itself, its physical structure on a microscopic level, acts like a collection of tiny prisms or mirrors. It separates light through interference effects. Think of like the rainbow sheen on a CD or a soap bubble, tiny, perfectly spaced grooves or layers. Light waves reflect from these various layers or microstructures. Some waves interfere destructively, they cancel each other out, while others interfere constructively, they amplify each other, resulting in these really vibrant colors. And here's the surprising paradox, the really neat twist. While blue pigments are incredibly difficult for nature to produce, blue structural colors are actually relatively easy to create. Conversely, producing red and yellow through structural color is much, much harder. So the dazzling blues and greens of peacock feathers, many butterfly wings, those iridescent beetle shells, that's all due to structural color, not pigment. Even human blue eyes, which is fascinating, they actually lack blue pigment entirely. Their color is purely structural, just a result of how light scatters within the iris, a phenomenon called Tyndall scattering.
Wow, that's incredible. So when you see a brilliant blue bird or, yeah, even look into someone's blue eyes, it's often not a pigment at all, but this clever trick of light physics. It really changes how you think about color, doesn't it? Okay, so let's circle back now. Let's revisit that initial provocative claim about ancient people not perceiving blue. This idea is often linked to something called the Sapir-Whorf hypothesis, or linguistic relativity, which basically is the idea that the language we speak might shape how we think and perceive the world. The strong version of this hypothesis suggests that if a language lacks a word for a color, people speaking that language might not truly see that color. It's a very compelling idea, but does it really hold up? Especially for blue.
Yeah, it is compelling, but it's important to directly address and, frankly, debunk the strong version of the Sapir-Whorf hypothesis when it comes to blue perception. The key thing is our human trichromatic vision, with its distinct receptors for red, green, and blue, well, it actually evolved around 23 million years ago. This means our primate ancestors, and by extension, ancient humans, were fully biologically capable of perceiving millions of colors, including blue. This isn't some recently acquired ability we just stumbled upon. And furthermore, the idea that blue is that rare in nature, well, it kind of overlooks the massive, obvious presence of the blue sky and the vast blue ocean, doesn't it? So it's not a matter of biological perception. How do we explain those ancient linguistic observations, like Homer's wine dark sea? Well, let's take that example. First off, ancient Greek wine wasn't always red. White wine definitely existed. But more importantly, the term might have been a poetic or metaphorical description, maybe describing the sea's appearance under certain stormy or twilight conditions. Or it could even be a mistranslation that solidified over time. The original Greek word enos likely had a broader meaning, maybe relating to sparkle or depth, not just wine dark as we tend to translate it today. It wasn't really until much later translations, like 19th, 20th century, that it consistently became wine dark. And more broadly, it seems ancient Greeks often described colors based on the feeling they evoked or maybe the quality or movement of light, rather than assigning a fixed abstract name like we do. For instance, they might use a word like aiulos to describe the shimmering, fast-moving quality of light on water, or maybe koulos for the gleaming metallic light reflecting off a polished shield. This isn't necessarily a lack of perception, it's just, well, a different way of categorizing and expressing the visual world. And actually, we do have evidence that ancient Greeks used words that likely meant blue. Simonides, who lived back in the late 6th century BCE, he described the sea as dark blue, using a specific term. And later, in the 1st century CE, Pliny the Elder used a Latin word for blue, caerulus, to describe a blue flower, a species that's still known today by a name incorporating that very term. There are also instances where, simple misunderstandings can arise from our modern perspective. One reason some scholars thought the ancient Greeks had limited color perception was their description of the sky as bronze. Now, today, we typically think of bronze as, brownish, metallic, like statues. However, if you look at pure oxidized bronze, it can actually appear quite sky blue. So their description might have been much more literal and accurate than it initially sounds to our modern ears.
Ah, okay. So it really sounds like while language certainly influences how we categorize and discuss the world, maybe how salient certain things are, It doesn't actually change what our eyes are biologically capable of seeing. The idea that ancient Greeks couldn't perceive blue, while a truly fascinating story and a great starting point, it seems to have been largely clarified by, well, a deeper scientific and linguistic understanding. It's more nuanced. We've truly embarked on quite a deep dive today, haven't we? We explored that captivating, if maybe ultimately flawed, claim about ancient color perception. We delved into the complex science behind why blue pigment is so rare in nature, but structural blue isn't. And we kind of uncovered the truth about how our brains and eyes truly perceive the vast spectrum of color.
It really does reinforce that color is just this profoundly complex phenomenon. It's a beautiful blend of physics, biology, and culture. It's not just something out there in the world simply waiting to be observed. It's also very much in here, in our unique human perception and how our brains process those light signals and make sense of them.
Absolutely. So the next time you look up at a vibrant blue sky or maybe gaze into someone's blue eyes, take a moment to consider that intricate dance of light and biology and physics happening that allows you to experience that specific color. It's an everyday marvel, really, isn't it? Makes you wonder what other everyday phenomena might hold such hidden depths if we just knew where to look and what questions to ask. Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.